Welcome everyone that has attended or joined so far. Go ahead and I would encourage you to use the chat box to let us know where you're at today. Welcome, Matthew. Hello, John.
Check out the Groupon app where you can save up to infinity. Theoretically
Welcome,
speaking.
Pat.
Actually, you can save up to $100 a week on what you do every day. Suppose you saved $10 on tacos and took that $10 and used it to get more great restaurant deals on Groupon, like Italian or Chinese. Pretty soon, you could save a ton. Brunch? Check Groupon. Dinner plans? Check Groupon. Hungry? Use the top-rated Groupon app to save up to $100 a week on what you do every day. Download the app and save. Groupon.
Are you frustrated by hidden wireless fees?
Please excuse the commercials. My Pandora is not a paid subscription. They are determined that they have to have commercials. I'll try to mute during those. Welcome to those of you that have recently joined. I would encourage you to open the chat box and let us know where you're joining from. We're glad to have you here. Welcome, Joe and Dylan. And hello, Kelly. Thanks for joining us from South Carolina. From New York. get started right at 1:30. If you are so inclined, go ahead and let us know where you're joining from in the chat box. And for those of you that have already done that, for those that haven't been in here, that chat box just gets started right when they come in. So they will have missed it. Feel free to introduce yourself again. Welcome, David. Hello, Michael. Welcome, William. All right, it is 1 o'clock. I'm going to go ahead and take away the music and we'll get started here. Welcome, Bernard. And you can continue to join us in introducing yourself throughout this introductory presentation, and I'll welcome all the speakers and welcome to everyone that is attending today. I'm going to go ahead and get started with a little bit of an introduction and background of our webcast series. These webcasts are one of several outreach efforts by the Livestock and Poultry Environmental Learning Center. Our purpose is to connect experts with those assisting producers and provide on-demand access to the best science. This webinar is being recorded and will be available on demand at the website shown on your screen at lpelc.org. Many of you are aware that there is an opportunity to receive continuing education credits by viewing the webinar. You should have been able to enter this information into the registration form before you joined the webcast, but if for some reason you missed that opportunity, you can contact me at the web address or the email address on your screen, leslie.johnson@unl.edu. ARPAS members can report their attendance at the ARPAS website, and other technical service providers can also request an attendance list and information about the webcast by registering at that link before or by contacting me directly. Our next webcast will be in September, and it will be focused on manure safety. Details for that webcast are still being developed, so we'd encourage you to check back on our website and find out exactly the date of that. It will be on a Friday afternoon like today's webinar is, but it's not yet been set which Friday we'll be doing that. You can ask questions in the question and answer box at the bottom of your screen. If you scroll over, there will be a Q&A box, and you can certainly use that at any time. You can ask questions throughout the entire webinar during anybody's presentation. If you would like the handouts, they are available at the web address on the screen, which I'll put in the chat box after our first speaker gets going here. In today's webinar, we have Nick Elger, who is here from the EPA AgStar program and the Global Methane Initiative, and he'll start us off today. And then we have Kurt Gooch from Cornell University. And I should have mentioned here that all of the biographies, if you want to learn more about the presenters and their contact information, are available on the flyer, which is available on our website. So you can do that at a later time. We also have Mamoun Sharara from the University of Wisconsin. And I got your name right. I'm so excited for myself. And Becky Larson, also from the University of Wisconsin. And they're all going to talk to us today about anaerobic digestion systems. Before I hand this over to Becky, I do want to do a little bit of a poll here and find out what everybody's experience is with anaerobic digestion systems. So if you would go ahead and answer that question while I turn this over to Becky, and sorry, not to Becky, to Nick, and he'll get us started. Go ahead whenever you're ready, Nick.
Okay, thanks, Leslie. Screen here. All right, are we on? Okay, good. Well, thanks, Leslie, for having me today, and thanks everyone for joining today. I'm really excited to be here with you today and share a national perspective on the anaerobic digester industry from the EPA AgStar. we're really proud to partner with the University of Nebraska. EPA AgStar is a voluntary collaborative program that partners with states, universities, and nonprofits to promote the anaerobic digester industry across the U.S. And we rely really heavily on our partners to get a good grasp of what's going on the ground across the country, and to learn about what we can do to help promote the industry in the U.S. And so today I want to talk with you about innovative business models for anaerobic digestion and some success stories of projects across the country that hopefully some of you that work more closely with projects can help emulate and learn from those successes. So some of the business models that I want to share with you today are third-party owned and operated systems, taking advantage of eco-markets for co-products, and utilizing renewable natural gas for vehicle fuel from manure-based digesters. Before talking about those success stories, I want to share with you a map from the EPA AgStar website. This is all of the livestock anaerobic digester projects across the country. Encourage you to go to AgStar's website. This is right on our homepage, and take a look at projects in your state or across the country to learn more about them. A lot of great information, really interesting about feedstocks and types of end uses for the biogas. So currently in the United States, there's 244 livestock anaerobic digester systems, majority of which are on dairy farms, and also swine, poultry, beef, and a combination of those. But there is a massive potential for additional livestock AD systems across the U.S. AgStar estimates that an additional 8,000 anaerobic digesters are possible on farms. And if that biogas is fully realized, could be a huge potential of 250 billion cubic feet per year of biogas, which is enough to power 1 million American homes' electricity needs for 1 year. And the great thing about biogas is that it's a flexible fuel, can be used both to generate electricity, but also used as a vehicle fuel. And if that biogas is fully realized from those additional digesters, 2 million passenger cars could be powered. So what's currently happening in the U.S.? So over the first part of the 2000s, we saw large growth in the number of anaerobic digesters. But in the past several years, digester growth has slowed down. So why is that? Well, a lot of reasons, and I'm sure many of you on the call or on today's webinar are very familiar with some of these challenges that digesters are facing. Low energy prices with the growth in the natural gas industry cause competing prices for natural gas to fall, which cause all energy prices to be very low. So building digesters has been challenging economically to put energy back on the grid and compete with the low energy prices that are there. Low milk prices as well too make it really challenging for farmers to access loans through their financiers. Interconnection hurdles are always a challenge, very confusing process often for farmers and definitely project developers. Each state has their own interconnection process. Each utility has their own process. So it can be really challenging to overcome and try to weave their way through the interconnection. And then renewable fuel standard uncertainty, both with the long-term viability of the renewable fuel standard credits for biogas, but as well as the fluctuating prices in renewable energy credits make it difficult to forecast out the long-term payback for accessing those financial incentives. So what can we do? What can we do to help grow the anaerobic digester industry? Well, we've got to think outside the box. Yes, Mr. Business Cat, beyond the litter box. So that brings me to some successful, innovative business models that help take advantage of diversified revenue streams and share risks and rewards among the farmer, project developers, and other partners. So third-party business owned and operated systems, eco-markets, and renewable natural gas to vehicle fuel. want to start with talking about Barway Farm in Deerfield, Massachusetts. This is a brand new anaerobic digester system built on a small dairy farm there. About 250 cows are feeding this digester, but they're also bringing in a lot of offsite food waste to the digester, and they're exporting the electricity produced to the the grid. So here's a little process map of the business model itself. Vanguard Renewables is a third-party organization that develops, owns, operates, and has invested in the digester itself. And they do all of the work to help take the pressure off the farmer when developing the project. So they coordinate with the food waste producers, the waste haulers, the utilities to interconnect, all the permitting, and everything that goes into making the project successful. The farmer has invested a small capital into the project and provides the manure feedstock and, of course, the land for the digester. And the food waste producers both provide the food waste to the digesters, but they also receive back the renewable energy that's produced from that system. And at the same time, the manure solids are separated and used as animal bedding on the farm, and the digestate is used as fertilizer on the farmer's field, which again grows the crops to feed the cows. So it's a really closed loop cycle, and they've had a lot of success there with that third-party model. Eco markets for co-products. One example is Magic Dirt. It's a potting soil product that's produced from digested manure. So they have partnered with 19 farms across the U.S. to separate the manure solids and put it into a package that they sell across the country. They have plans to be on the shelves at nearly half of the Walmart stores in the country by the end of this year. And they have done some testing on their product. And many of you on the call, I'm sure, know that digested manure is gold for plant growth. And they did some testing that showed that their product has more nutrients and outcompetes some of the other soil products that are on the shelf. So one company that's taking advantage of the digestate to enter into a market to help diversify revenue for farmers. Another great product is cow pots. Freund Farm in Connecticut. It's a very small farm. About 300 dairy cows are feeding their digester, and they separate their manure solids to create biodegradable planters. So these planters can replace unsustainably harvested peat moss or petroleum-based planters, and it's a really great product that takes advantage of manure solids that would have just gone onto the field but creating another additional revenue stream from their digestate. Fair Oaks Farm in Indiana. It's a large farm that's taking advantage of renewable natural gas and powering vehicles there. So they have about 12,000 cows plus swine feeding their digester. So it's a very large system, but they're compressing natural gas and fueling milk trucks that are hauling their milk to across 3 different states, and they're displacing a lot of diesel fuel in the process of doing that. Hilarity's Dairy in California is also taking advantage of compressed renewable natural gas to fuel their vehicles, and they're fueling 2 milk trucks and 6 on-farm vehicles, pickup trucks around the farm. So it's a really great farm that they have there, taking advantage of renewable natural gas. And many of you, I'm sure, are aware of the opportunities that exist in California to help finance some of these projects. California has a low carbon fuel standard credit that many people are taking advantage of, and as well as the renewable identification numbers through the RFS system. So if farmers do use vehicle fuel from their biogas, they can generate economic incentives from that biogas. California also has put out this past year is going to put out $50 million in grants for anaerobic digesters and other advanced manure management systems to help reduce greenhouse gas emissions. So there's a lot of growth that we're seeing in the renewable natural gas vehicle fuel from dairy manure across the country. The great thing about renewable natural gas is producers can lock into the long-term fuel prices and don't have to worry about the ups and downs in fuel prices. And of course, natural gas burns much cleaner and quieter than diesel, making it more desirable for vehicle operators. So if we're going to tackle some of the biggest challenges facing the country in terms of reducing greenhouse gas emissions, nutrient overloaded waterways, nutrient deprived soils, we've really got to think big about how we can help move the anaerobic digester and biogas industry forward to tackle some of those challenges. So when thinking about those, here's just some examples, aspirational examples that I think we can all work towards and think big and try to achieve. I mean, imagine if all the dairy and the meat produced in the US was hauled by renewable natural gas vehicles. It's possible, as we're seeing some farms utilizing that renewable natural gas. 50% of the fertilizer market replaced by manure-based products. What if all of the dairy fiber replaced unsustainable peat moss? We showed earlier that 8,000 farms are possible to have anaerobic digesters. A good first step would be, how about 1,000? Very well possible. And the US EPA and US Department of Agriculture has a goal of reducing our food waste by 50% by 2030. And it would be great, and we're already seeing it, food waste going from landfills to on-farm anaerobic digester systems. So just some of the takeaways. Technology is always important, but a business model that can take advantage of diversified revenue streams is really important and can help drive projects forward. Entering into eco markets, renewable natural gas markets can definitely help make systems possible and profitable. So thank you very much. I encourage you to visit the AgStar program website to learn more about anaerobic digester systems and about the great work that we're doing to try to help move the industry forward.
Thanks so much, Nick. And remember, you can ask questions at any time, and you are certainly welcome to do that in the Q&A box. Next up, we have Kurt Gooch, who's going to talk to us about estimating the economic value of the greenhouse gas reductions that are associated with anaerobic digester systems, specifically in New York. Correct, Rick? Or Kurt? I'm sorry. I don't know why I said Rick.
That's correct, yes.
All right.
And in similar states as well.
All right. So go ahead whenever you're ready, Kurt.
Okay. Oops. Started way too soon. How did it happen? Okay, so everybody, thank you for the time. I appreciate the opportunity. And I'm going to go through a summary of quite a bit of work we've been doing here in New York State, which again, as I mentioned a second ago, would apply to other similar states in the Great Lakes area relative to the value of greenhouse gases that would be reduced by using an anaerobic digestion system. So Peter Wright and myself, who's listed here as well, have spent a lot of time working on this. I get the pleasure and opportunity to present this to you this time, and I acknowledge Jason Oliver, who also has put effort into to the work. So take-home points: manure-based anaerobic digesters provide more value to society than the current revenue streams they provide or they receive. The numbers I'm going to give you are not absolutes. Lots of variance at the farm level, so I want to emphasize this focus on just the general trends and not the overall values in every case. Definitely more work's needed to that would include communicating the values and lobby for change. So we're going to go through a brief summary of anaerobic digestion in New York. We're going to talk a little bit about what New York's done recently in the last 3 years, moving away from a RPS standard, Renewable Portfolio Standard, into a clean energy standard, and how that's affected our work in anaerobic digestion. So I'm going to talk about quantifying the greenhouse gas emissions on New York State farms with digesters, and look a little bit at the value that those reductions are if we apply the EPA social cost of carbon. So as already been mentioned, there's comparatively few digesters in the country compared to the number of farms. Last time I checked, which has been a few years ago, there was about 100 intensively managed anaerobic digesters in the country. And so those are digesters where we're actually putting heat to the digestion vessel and trying to maximize gas production. Those are the kind of digesters that we work with a lot in New York, or solely in New York and the Great Lakes states as well, as opposed to covered lagoons, which would have been included in EPA numbers. So we're not representing anything with covered lagoons. New York's had a slow, steady growth of digesters over the last 18 years or so, and started off with one farm in 1998. And we're now at there's actually about 32 to 33 operating digesters now in 2017. So still slow, steady growth. And there's some reasons why we're this number of digesters, around 30 or 32, and about 4,800 dairy farms today. And that is because the economics associated with a digester need to be improved overall. It's the case across the country, except maybe in Vermont. So in general, the total annual cost to own and operate a digester exceed the total annual benefits, whether it be monetary benefits or displaced cost. And so that fuels our fire here in this group at Cornell to keep working on things. We recognize that dairy farmers cannot use too much from their milk receipts to pay for large capital and expensive operating cost investments like anaerobic digestion without some meaningful revenue. So along those lines, we spent a lot of years thinking about what could be done differently. This includes some vision that we articulated at a meeting that was the New York Cow Power meeting that was put on by DMI several years ago, and looking to tie anaerobic digester-based system into the community. Not as easy as it looks. We did actually looked into the specifics of doing that in the town of Lowville, where, among other things, the Kraft Philly cheese plant is located, and several farms. So this is a cover page from a report that we put out for a feasibility study. And in essence, that system could have been viable, economically viable, if about 1/4 of the tipping fees that is normally associated with landfills actually went to the digester instead of the landfills. We've also looked at partnering with digesters with greenhouse gases very extensively. Tim Shelford, who's in this group here, has developed a real nice model on that, which includes economic projections, and it's something that may hold some water down the road. But we firmly believe that anaerobic digesters provide a lot of benefit to farms and non-farms alike. We have this famous saying around here of our Appendix A. And Appendix A is basically 2 pages about all the benefits anaerobic digestion provides. So with that said, we keep looking at ways to bring more value to the farms for anaerobic digestion. And recently, as I mentioned a minute ago, our state started moving away from the RPS standard into a clean energy standard. And there's some pretty envious goals by way of statement by some of the state officials. So we said basically anaerobic digesters are in a good place to help the state achieve some of these goals. Greenhouse gas reduction to 40% between 1990 and 2030 levels, and even higher reductions by 2050, along with very meaningful renewable energy in the state by 2030 being 50%. So quite a ways to go, and so anaerobic digesters and farms are really interested in that. The model in New York State, as it was most of the country of yesterday, is centralized power. So big power plants transmitting megawatts or gigawatts, if possible, I don't know, to outlying areas and being distributed. Tomorrow's vision in New York, anyway, is to decentralize and go with more local clean power. So another thing the state has a goal in that we see where digesters can fit really nicely. So with those two top bullets being covered, we'll jump into really what's the meat of this, and that's the quantification of greenhouse gas emissions from farms in New York and similar states that have anaerobic digesters. So the approach we used is no different than what's basically used when a farm is looking at or is participating in the carbon market. We basically calculate the greenhouse gas emissions associated with a baseline condition, and then we subtract from that the change in those emissions based on implementing an anaerobic digester. And so on our baseline side of things, this one picture basically represents the boundaries of our analysis. We look at all the energy. In this analysis, we look at all the energy that was being used, electrical energy that is, at the farm to milk the cows, cool the milk, ventilate the barns if that's the case, certainly cow cooling, pumping water and things like that. We also looked at the emissions associated with the long-term storage. So there case the methane and maybe some NO2 emissions depending on the conditions. We do not include CO2 specifically here because it's a neutral emission greenhouse gas warming potential of 1, and it's being recycled above the Earth's surface, so no need to account for that. So if we break this up, typically farms in our area use about 1,100 kilowatt hours a year per cow. And the greenhouse gas emissions with generating that much electricity in New York State, we have a special number. We're different in New York. And so if we use that CO2 equivalent emission and multiply by the kilowatt hours per year per cow, we, excuse me, I have to make sure my computer software doesn't shut down here. We have a 0.58 megatons of CO2 equivalent per year for the fossil fuels used. Then we get into the emissions from the long-term storage, and we use the IPCC Tier 2 method, so International Panel on Climate Change, and the factors that go into that are what are the mass of volatile solids. That's some of the energy in the manure that's basically converted to, can be converted to biogas. We look at the potential for that conversion. There's a conversion factor, and then there's some site-specific factors or location-specific factors depending on the temperature. So that's the methane conversion factor. So if we crank the numbers out for a typical manure storage in an upstate New York, we calculate about 4 megatons of CO2 equivalent per year. That's on a per cow basis. And then if we include N2O, basically going through the same IPCC Tier 2 method using an equation specifically for N2O, 0.38 megatons per CO2 equivalent per cow year. So basically the emissions associated with our boundaries in this case are those from the electricity running the barns and milk harvesting and cooling the milk, and those associated with the long-term storage. We're at just under 5 metric tons of CO2 equivalent per cow year. So next thing we do is we basically say we're going to take and insert a anaerobic digester, which is this long, narrow rectangle here between a long-term manure storage and our cow barns. And so then we're going to basically look at that anaerobic digester very carefully. There's a lot of factors there. There's a lot of judgment calls, professional judgment calls that are needed to come up with some answers that could be defendable. And we've done our darndest to do that as best as we can. So we're not overrepresenting or underrepresenting or misrepresenting anything. We're trying to use a very balanced approach here. So if you were to think about all the variables and then different ways you could look at them, there's a conservative way. So the anaerobic digesters, normal management with no emphasis in greenhouse control. Those would be a lot of the digesters in New York State and the US for that matter, because to the recent past and even locally here, there's been no significant value for greenhouse gas reduction. So farms are not incentivized to maximize the greenhouse gas reduction. Achievable would be ones that would be under excellent management with emphasis on greenhouse gas control. So we tend to go with higher values there. And then typical may be ones that probably are ones that were more readily achieved if people put some really good effort into it. So those are the other numbers, which I'll call out. We're still using for those of you know electrical generation, we're using a pretty aggressive capacity factor for even where we're talking about this typical line of 0.95. So this is the flow diagram So we have a dairy facility in the lower left-hand corner, our anaerobic digester inserted between that dairy facility and a long-term storage, and we've included a solid liquid separator as part of our anaerobic digester system in this analysis. The reason we did that is most of the farms that have digesters are also very interested in using reclaimed manure solids for bedding, or they already are. So in this case, we decided to include that in analysis. I will say that not all farms are interested in that because of challenges that are associated with using organic bedding relative to udder health and milk quality in some cases. So my goal is not to go through all these numbers here, but to show you that we have looked at all the numbers for all the factors using a conservative, achievable, and a typical approach. So we went back and forth quite a bit on this. At the end of the day, if we use the typical approach and we basically add up and subtract off what the baseline, so I didn't say that very clearly, we basically had a baseline of 0.49496, if you recall earlier. That's per cow per year. And if we look at our digester system, we're now not purchasing fossil fuel-based electricity. We're generating ourselves. So that's a green number. But wait a minute, we still have emissions from the digester. They're not perfect as far as containing the gas. There's some unburnt methane that would maybe go through the engine, very small, but we accounted for it. Our flares aren't perfect. System leaks. Anytime you see a digester and see corrosion around it, that's a leak of biogas. So that's a little bit more hefty number. We do see system leaks, and so we accounted for those. And then our long-term storage, we're not totally mitigating the greenhouse gas emissions associated with long-term storage, but we are greatly reducing it. And we've used the IPCC Tier 2 equations and came up the 1.87 number using typical values. So again, if you basically follow along, we basically are subtracting our reduction to the system from our baseline, and get a pretty nice reduction there of almost 4 metric tons per CO2 cow equivalent a year. The last thing I'm going to do is take that number and apply the EPA cost of carbon, or the economic value of carbon, depending on how one would look at it. Right now, it's more thought of as a cost. So we have our 3.9 megatons of CO2 per cow year. And we multiply it by an average value of $47.82, which we basically calculated over the last 3 years. Actually, it's not the last 3 years, it's the 3 years starting with this year going forward, and that's relative to some specific work we did for the state government. And in this case, we have $186 per cow year. So that's some meaningful dollars. That would definitely change the economic situation on a dairy farm relative to the anaerobic digester business enterprise. So if you are interested in reviewing the engineering and IPC equations and math and the stuff associated with calculating these numbers, we did present a paper this summer at a professional society meeting that we could make available in the near future. So again, the take-home points are, I'm just going to reiterate them, that we need some help. Farms need some help making the digesters more economically viable and stand on their own 2 feet. These numbers I have provided for you are not absolutes, so we need to keep that in mind, and certainly have some more work to do to confirm the numbers we have and then lobby for change. Even if our numbers are off by 30%, they're still pretty strong numbers that would mean a change in the overall business enterprise for a farm-based digester. So with that, I conclude. Thank you for your time and appreciate the opportunity.
All right, thanks so much, Kurt. Now we have Mahmoud Sharara from the University of Wisconsin again, and he's going to talk to us about the assessment of coordinated anaerobic digestion for smaller dairy operations. So Mahmoud, whenever you're ready.
Thank you, Leslie. Thank you, everyone, for tuning in.
You might need to speak up a little bit more. Your microphone's not coming through very loudly.
Sure. How about this?
A little better.
Okay. Good afternoon, everyone, and thank you for tuning in. My name is Mahmoud Sharara, and I'm a postdoc scientist here at the University of Wisconsin-Madison. And I'm glad I'll get a chance to share with you some of the research that we are conducting here in the anaerobic digestion systems in manure farm, in livestock production in particular. I'll start with this news clipping here from a recent call for proposals here in the state of Wisconsin about funding for clean water renewable energy systems on farms. And that proposal emphasized the interest in cooperative systems that serve more than one farm at the same time. So there are many words or terms used to refer to that: coordinated or centralized or cooperative. But basically, we are referring to the same concept here. So one of the key issues that we set out to answer in this research, and I will show you here, is how to go about developing these systems. Should we pick a farm arbitrarily and draw a radius around it? Or should we start by a region and try to convert everything in that region? So that's one issue, how to go about developing the system here. The second point is the uncertainty inherent in a system like that. There's so many parameters or variables, and with each one of them changing, the feasibility of the entire project changes. So to answer those two issues, we set out to develop this modeling study. So there are pros, of course, to using this coordinated approach. You reduce the cost of processing per cow or per unit animal. You can get more participation, more reduction of greenhouse gas or more energy production, so on. But the downside is the logistics, of course, can be tricky. So again, so the question we set out to answer is, what are these parameters and how they control the profitability? Does centralization offer an advantage? And what are the general rules we can deduce about these systems? So we picked out two dairy production regions here in Wisconsin. You can see them highlighted. Region A, South Central Wisconsin, around Madison, and the other region here is around on Lake Michigan. And we have the data on farming on both the regions, number of cows and number of farms and so forth. In this slide here, I want to draw your attention to a few things. These dots represent the dairy herds in the two study areas we are talking about, the South Central and the East Central. The first point is the number of farms is more or less comparable, 156, 151, but the number of cows or lactating cows is not the same. There's a significant difference between the two. Also, the distances between these farms is not uniform. Here, the farms are more clustered, more farms clustered, less farms spread apart, but more cows and less cows. So with that in mind, I present that in a different way. We look here at the herd distributions. So we see in the South Central one, most of the herds are 200 to 500 cows, whereas in the other region, it's mostly larger CAFOs, 3,000 and above. We also look at the distances between farms. That's a key parameter when we look at aggregating manure to process into biogas and digestate. So we see, again, the clustering. One of the regions have more cluster farms than the other. Again, to reiterate what the other presenters have shown, there are different ways or different flavors for adopting this system and end uses for the biogas. For the current study, we focus on biogas to electricity and heat using combined heat and power system for sale to the utility and to supply heating demand. And in this model, our assumption is all the heat generated is sold to offset natural gas demand, and the digestate is returned to the farms. So we set about selecting the parameters that drive the performance of these systems, and we classified them by type. So on the left here, you see the source. In this case, it's dairy farms. Our study limited to dairy farms. We didn't consider mixed feedstock streams, although this is certainly legitimate, and a lot of the times that's gives a huge advantage. But we're looking into the capacity of the systems, how many tons per day, what is the relative location, and what's the quality, what's the biogas potential. Then we look at the digester itself, what are the energy needs, conversion efficiency, generator. And then finally, we look at the economics of the system. What's the capital for the system, cost share or supports, and the revenue streams. In this current study, we look at the heat and electricity, but there are also other streams as Kurt pointed out, there's greenhouse gas credits. And in this case, we are using the prices that are available currently for offset tons of CO2. We also look at renewable energy credits, or RECs, as the common term refers to them. And one of the key challenges here is we can pick one value to represent each of these parameters, but in reality, they vary within a range. So to address this variability, we developed a new approach. We used our existing knowledge to develop ranges and not just one deterministic value. And then we sampled from these ranges a sample of 1,000 samplings. And then we used mathematical optimization to find the most lucrative of profitable system. We used a discounted cash flow system. We looked at the net present value of the entire project after 20 years. That's our assumption for the project life. And finally, instead of getting out one solution, we end up with a population of solutions. We analyze them statistically to see where are they clustering around. Are there certain common features that we can intuit from that? So that's a representation of the system. And again, all that is available in the handout, so I might move a little quicker here. Here are some of the values that we sampled from. As you can see here, these are ranges for biomethane potential, for capital costs, system performance, and so forth. And some of the parameters were held constant: the discount factor, project life, and so forth. So it is computationally expensive, but with clusters of computer we have available, whether on cloud or locally here, the time is not as demanding. Less than an hour, the computation could be carried out. So the results I'll share with you now are two parts. So there's a part when we compare the two regions that I highlighted for you. And then there are, within each of those regions, we look where the digester systems are clustered or available or profitable. So first, when we compare the two regions, you look here and you see that the blue part here represents where the systems are lucrative. So for the 1,000 times we try to find the most economic systems, majority of the time, in both cases, it was not economic within the parameter ranges we've identified to build an AD system to generate profit. So that's a little bit of a bad news. You see here the difference between the two regions. Certainly in the region where the farms were larger, it was more profitable. It was more frequently the case that an AD will be profitable there than in the smaller, more clustered farms. So that's another insight. Within these systems, we have other data, and that's in the manuscripts that is already undergoing. But not all of these systems were cooperative, which means not all these digester systems, the 42% or the 13%, were cooperative projects. Most of the time, there were actually single digesters on one farm, serving one farm. 15% in this case, and 10% in this case, these systems were actually cooperative, one digester serving more than one farm. Another thing we looked at is the distribution of the net present value allocated to a cow, so dollars per cow over the entire project life. So you have to divide that over 20 to get the dollar value per cow per year. And as you can see here, it's not incredibly lucrative, and most of the values are clustered less than $5 a cow a year. When we try to break down the costs, operating and revenue, you see the labor and maintenance dominate the cost. Transportation, in the case of cooperative management, is more so the case in the South Central than in the Eastern. And the revenue is dominated by electricity revenue. Another part here, we define some ranking criteria for the digesters, what is the probability of a digester being built on a farm, and we rank them in a descending order from 100% and going forward. And we also looked at the ranking of the farms participating in these clusters for cooperative management. It'll make sense when we look at the maps here. So before you get startled by so many details and points here, I want you to look here on the left side. Here we are maximizing the profitability in the south central region here in Wisconsin. These are the farms available for digestion. And the whole circles represent the farms. The black circles represent the digesters. And the red lines represent all the farms that are aggregated to that digester, that are cooperatively participating in the digester. You see, not all the digesters have the same probability, so that's the first takeaway. These digesters are located on the largest herds. That's number two. The radius for these digesters is not the largest, is around 1 to 2 miles. And a majority of the time, these digesters are single, as in they do not bring whole manure most of the time from the other farms. So these are the most profitable systems, if profitability is the goal. Here, when we actually target the greenhouse gas reduction as the maximization goal, you see the provided that the profitability does not go negative, so we can sacrifice the profitability to zero, but maximizing greenhouse gas reduction. You see the radius for aggregation grows. You see a new system pops up here. That system is the lowest frequency. It shows up the least number of times, and it's highly dependent on the surrounding farms. In the same way, we look at the second study area, and we see the clusters when we target profitability maximization, and then when we target the greenhouse gas reduction. So some of the takeaways from this, these figures and of this study, we find that the profitability of digesters using dairy manure exclusively for electricity sale is not there yet. It's tenuous economically. The profitability of cooperative digesters are driven by herd sizes locally and the spatial distribution, of course. And we also find that both individual and cooperative digesters are always anchored, or the hubs are on the largest herds. And we found that the cooperative digesters, in the case where they are built, they show the highest net present value per cow in any of the options that are available in that frequency. Our goal going forward is to incorporate other food waste stream and to allow for other ways of utilizing the biogas. And finally, I'd like to acknowledge the funding sources and other consultants we used their expertise. Thank you.
All right, thank you, Mahmoud. And next up and lastly, we have Becky Larson, and she's going to talk to us today about integrating small-scale digestion systems in developing regions. So, Becky?
Slow at clicking. I'm hoping you can see my slides.
Yep.
All right. So good afternoon. Lovely Friday in August. I'm going to talk to you today about quickly just integrating small-scale digestion systems in developing regions, taking a little bit of a different road than we've heard from some of our other great presentations this afternoon. So I just wanted to share with you a little bit about these projects. And here is one of the groups that I work with in Uganda. I'm talking a bit about these lately because we kind of have come to, after a few years of research and work and assessments and development, we've kind of been able to do some review over what we've done and are aligning ourselves for where we want to go in the future. I think our projects have been pretty successful, and one of the biggest reasons that I tell a lot of our grantees when they ask us how we manage to get so much done is our project teams. Working internationally proves to have a lot of challenges, much more so than we're used to at home, even though those always provide a lot of challenges. So I think picking a good team, generally the teams I've been working with have been relatively young and have a lot of passion for what they're doing. And so we've seen them be very successful. In addition to the groups we work with in Uganda, we also work with, I keep skipping that one, some in Bolivia. So we have some projects in South America. And we also have some partners in Rwanda. So we're trying to expand some of the lessons we've learned in certain regions and try to move them to others. It's been really great to see the groups from Uganda and Rwanda kind of getting together. They've learned a lot from each other, of visiting each other's sites. And that served as a really great way to energize them to do some different things. For example, in Rwanda, they had some really great demonstration gardens and had a great way that they set up how to do some educational courses about cropping systems. And so the Ugandans were very excited to take some of that information back and work that into their system. So I think it's really a great idea if we can try to cross some of these projects and introduce some of these folks to some concepts going on in other places. So digestion systems in developing regions are very similar to the ones we see here. Most of the systems that we work with use some kind of manure from animals. A lot of these animal facilities are very small, maybe just a few animals. We have a lot of food waste being produced at markets. Some of our new ideas after we've kind of seen everything that's happened is that we would really like to integrate more systems into these market areas. It can pose some challenges in some countries. As you can imagine, there are people who are covered to handle certain waste streams, and then you have overlapping layers of government. I think sometimes it's even hard for us to figure out how things ought to move forward in our own countries, which is another reason you need a really great team. I can't go to Uganda and figure out the structure there very easily, but I certainly can rely on my Ugandan partners to figure out how they may want to integrate and what kind of situations would pose that we might have some success and others that are probably unlikely to work very well. They have a lot of slaughterhouse waste. That's another thing about the markets. Most of these slaughterhouses are located in the markets. The majority of it ends up in rivers and streams. So part of the reason that we sometimes want to introduce these digesters is to try to promote some increased effluent management. That doesn't always happen. I'll talk to you a little bit about some of the challenges there. But in addition to producing energy, it helps to kind of pull these things together so they don't just get lost along the way, as you saw with the market waste just kind of left in the street or just piling up or being pushed into the streams or the waterways. The systems can be very basic. I think one of the challenges of going from somewhere where we try to do lots of things where we're trying to reduce labor is going into an area where you need to know better what is the expenses and what does labor cost. And in many places like Uganda, Rwanda, Bolivia, the labor is actually very low cost, and it would be better to encourage more job production and maybe less technical or advances in some of the ways that we do things. So while there are many ways that we could better collect feedstocks, it is still the cheapest and most effective to have folks ride around on their bicycles or bring them by hand from neighbors. A lot of our systems also integrate human waste. That poses some additional challenges due to the fact that you have a little more concern about the effluent and how it's being handled from human waste. But we see that at a lot of places where the digesters make sense, where it's large enough like a school, handling human waste is a problem. And so they want to be able to gather some of that. They have the resources to come up with the capital, as well as they would like to recoup some of that operating cost by taking advantage of some of the gas to produce, say, food at a hospital or food at a school or something in that manner. We have lots of different designs based on the region. We've learned a lot that if they have expertise or ways they like to do things, we like to stick to that. So this is an underground dome design that they use in Uganda. This is a digester design that's above ground. It's made from a water tank in Bolivia. It's important to look to the partners and modify things based on what they have available, the cost of materials, and sometimes what has worked before or what people have tried that had failed. In Bolivia, I know, the bag digesters, although they're much cheaper, they had a lot of failed experiences with that due to this is right near the Amazon and the amount of bugs there had eaten those away. So it was important for us not to go along the lines of other failures. We have, in some places, we have to integrate biogas storage because like in Bolivia, it's very, very hot in the region we've been working. And so we produce some additional gas storage so that we can hold more gas and use it when it's available. Generally, we use the gas for cooking and many of the systems that helps us to reduce some of the air quality issues and the traditional way a lot of things are cooked. We do a lot of work. This is just one example from a paper, I think that was released just this month, where we looked at kitchen air quality and different kinds of feedstocks. And if, the biogas really has an impact on particulate matter, so you can really reduce the biogas. Unfortunately, if you use any firewood, we start to see that creep back up for the particulate matter. Now, there's lots of other things you can see in this paper about air quality that I don't have time to go over today. I think the biggest thing still constricting us from maybe taking some of the advantages, not only economically and trying to replace some of the other fuel that people use, but in terms of taking advantage of air quality related things, and maybe some other things, are that the digesters a lot of times are underproducing what a lot of the installers have quoted them as being. So we need a lot more education on how to operate them more effectively, and then additional practices to make them more efficient in terms of biogas production. We're doing things in that realm. So to start to look at, well, we need to give them what they need. Things need to be designed for the region. It's kind of a lot of failures we see are not taking the time to integrate into the communities and understand what they need. It's time consuming and challenging, but the output from it is really useful. We were getting things back from consumers like, this is the way we normally cook food, and this is the kind of stove you're giving us to work on. And so then we could integrate and maybe make a stove that's similar, but where you could have biogas in the top, but also change to firewood in case you didn't have enough biogas to cook your entire meal. One of the really popular things we've seen lately is the use of absorption chillers, so using the biogas directly for cooling. Those have been really popular in helping people to reduce their spoilage, particularly out in rural areas. Again, I mentioned before that we wanted to increase effluent handling. In some cases, we weren't seeing that was happening after we had done a lot of education and install. So we moved to some basic solid liquid separation, in which we've been able to recycle the liquid for water, so that not only reduces some of the handling issues, but reduces the need for labor to go get water, and adding a pretty valuable resource into a waste system like water is not something in a lot of these regions that they want to do. Then we have measured a lot of parameters, so looking at those kinds of systems, trying to educate and redesign to try to reduce maybe impacts of pathogens, or make recommendations for handling of the effluent once it goes out into the field. We've had a lot of success with doing some education and farmer trials. You can see here, this is a producer on the right-hand side of your screen is where he applied some digestate, and on the left-hand side is where he used his traditional practices. And so he was extremely happy about his results. It's pretty easy to have good results when you're compared to maybe traditional practices that don't use a lot of nutrients. But we also do a lot of field plots to look at how are we comparing if people use traditional inorganic fertilizers, what kind of rate should they apply? And we've seen pretty good performance, at least similar to inorganic fertilizers, if not better, in some areas of grain or stover weight production. We've also looked at just applying the solids. One of the things we noticed here was that maybe in drought years, it looks like actually logically putting solids may be much better than using the inorganic fertilizers or controls. So again, after all of this kind of thing, we think there are some really great benefits, particularly in places where they don't have alternative energy options. And actually, a lot of these digesters are more cost effective than maybe some other energy options, but we still need to find ways to increase gas production, to do a little more sharing of our information from region to region, and to do a little more education. And of course, funding and trying to find the capital costs is always a difficult thing in these places. So we need a little more invention on ideas on how we could move forward there. Okay, so that's all I have to share with you today. And I'm going to try to kind of go through some questions if needed. Let's see, there was one that was sent to Leslie. I think this one was for Kurt. I forgot to mention, Leslie would like you to answer her polling questions that pop up onto your screen if you wouldn't mind. And feel free to put some questions up if you'd like to. We are happy to answer anything that you saw in the presentations or generally about anaerobic digestion. I know you've got quite a few experts here that would be happy to answer your questions. So again, answer those poll questions. And I'm just going to start with the first one that I see here, was that how do you input your calculations for the digester energy heating needed? I believe that was a question for Kurt, if you have an answer for that one. Or I don't know if you need clarification or if that is good enough for you.
Sure, thank you, Becky. I think I can answer sufficiently. So the question is, for the analysis that I presented on the greenhouse gas reductions for the boundary conditions, how did we include heating for the digester? So good question. The analysis that we did was specifically on the greenhouse gases associated with the electrical energy used on the farm. And so we did include the parasitic electricity used to operate the digester in our analysis. So when it came time to looking at the renewable energy generated by the system, we actually subtracted off from the total renewable energy generated, the parasitic electrical energy to operate the digester. So we did account for that. We did not account for any heating of the digester. It was not part of the boundaries of the analysis. The reason why we didn't include it, other than it was not within the boundaries, the reason it's not in the boundary is because the heat of combustion from using the biogas to fuel the engine generator set is harvested and then used to heat the digester in most cases to about 100 degrees Fahrenheit. And so if that heat was not harvested and used, in if not all cases, it's just dumped to the environment right now, or dumped to the ambient. In other words, big radiators are used to transfer the heat from the engine to the outside. So we're merely just using heat that otherwise would be dumped to the environment. So we're not using any fossil fuel to heat the digester. So for those reasons, it's not included. We could have included in our analysis fossil fuel heat avoided by way of using that extra heat from the engine generator set not needed to operate the digester and used, for example, to operate a greenhouse. But we did not include any heat.
Thanks, Kurt.
Sure.
We had another question that says that someone was asking that these, like other renewable systems, are being discouraged from selling energy back to the grid since the new administration wants to become more reliable on coal. Can anyone speak to that? So I don't know if you or Nick or anybody has any idea if they've felt as though there's been some additional discouragement or maybe anything that's changed recently.
Yeah, I can give AgStar perspective on this. Certainly the new administration has made supporting coal a priority, but I'm not aware of any efforts to discourage biogas or other renewables. So,
any other comments? Okay, thanks, Nick. The next question was from Walter, and he is interested in about the cooling systems from the last biogas presentation. I think that's the absorption chillers. So the absorption chillers are a chilling mechanism that takes that direct burns into, I don't know, it's kind of like a chimney, and then it goes through like a heat exchanger in a way. And then it uses that to direct cool a unit. And in that particular case, we purchased existing units from China. The technology has been around for a long time. They traditionally run on natural gas. So typically, if you want to buy a pre-manufactured system, they have them in all sizes and you can get them around the world. You just have to modify them to be run on biogas. They have not been they've been pretty easy to implement, particularly in Uganda, because we had some history with people using kerosene coolers. And so the chillers were run in the same way, but the heat was produced from kerosene instead of from the biogas. So it's pretty simple. The nice thing about it is that the biogas being burned only touches a small part of the chiller itself. So if you have hydrogen sulfide or other corrosive components, your gas quality, I guess I'm saying, is not super important, and that it's easy to clean to figure that out later. All right, I'm not seeing a lot of other questions. Maybe one thing I'd like to ask of our panelists, of each of you, I know a lot of you touched a little bit on economics. I am curious if you have ideas of how we think we could move to more economically sustainable systems, or how you think we might pave a path into getting somewhere that we might be able to encourage more people to install digesters. Anybody want to take a stab at that?
I can start, Becky, if you like.
Yeah, that's great, Kurt.
Sure. So interesting question, and I would say that since we've been working on digestion for a long time, we've kind of learned where we need to be going, and where the opportunities are. At least we've learned some of those, I would say, and through our work, we've really kind of concluded that our efforts really need to be focused not as much as helping the farms on their digester projects, which is fun, and we get to do that from time to time. So that's really cool. But is to make it known to policymakers and others in the state about what these digesters really are doing, what they can do, and how some of the values for example, in this case, greenhouse gas reductions can be monetized, and then really improve the situation, so we would end up with more digesters. So we're not really very much going down the route of asking for subsidies or anything like that. It's more let's develop a business model industry platform that will stand on its own. So I've always believed for a long time that we're not going to be like Germany, where they get up to 32 cents a kilowatt hour for electricity, or whatever the going rate is at this point in time. Or maybe Denmark, where I like the Denmark model better. I don't remember all the items that were put in place, but the Danish have 9 items that they basically put in place that helped move the anaerobic digestion forward to where it is today, which is very impressive. And essentially, the incentives were targeted at improving things other than energy in the country, like improving water quality, and anything that was done to improve water quality that had a digester component that became a incentive for a farm to take advantage of that. So there was 9 things like that, which each little thing together ended up in a victory. So I like that model myself.
Great. Nick or Mahmoud?
Yeah, Kurt, you touched on a lot of good things there. Certainly, educating local and state policymakers on all of the benefits the systems provide is certainly an effort that AgStar continues to try to move forward with. And I touched a little bit on my presentation as well, as diversifying revenue streams, taking advantage of all the benefits that digesters provide. Energy at this point is not going to be a financial driver for projects. So trying to find value from the digestate is certainly an opportunity to help make projects viable.
Absolutely. Just to chime in, maybe in the first slide in my presentation as well, the driver here, certainly in the state of Wisconsin, for funding for these projects was clean water and renewable energy, in that order. And that sort of indicates how achieving more than one goal using these systems is the only way to have them implemented going forward. So bundling that with nutrient export, for instance, or certainly touching on the regulatory landscape, be it with the grid or be it with the funding or cost shares, these are about the only ways to push the technology forward.
Great. I appreciate everyone's insight on that. I I think it'll be a big combination of a number of things. I'm hoping in a few years we could do another webinar and give you some new projections of how well things have come. So I'm hoping everybody out there and those presenters and others continue the great work that they shared with us today. Leslie, I think we've come to the end of probably past our regular program time. Is there anything else you would like to ask of the participants?
No, I think everything went really well tonight, and I want to just spend some time thanking the presenters. And we'll see you all in September, I hope, for the manure safety webinar.
Great. Thank you, everybody.
Thanks, everyone.
Thank you.
Thank you. Bye-bye.